Have you ever really looked at the metal things all around you? I mean, your keys, the frame of your bike, even something as simple as a paperclip. They all started out as these kind of boring lumps of raw metal. So how? How do we get them from that raw state into these incredibly useful, strong shapes that literally build our world? Well, we're about to dive into the core processes of metalworking that make it all happen.
And to make this super clear, let's start with a really simple question. How in the world does a solid, plain block of steel become something as precise and as strong as a wrench? I'll tell you, it's not magic. It's actually a fascinating series of engineering steps that involve a whole lot of heat, a ton of force, and some incredible precision.
So here's the plan for our journey today. First, we're going to start with the most important thing of all, temperature. Then we'll hammer our way into forging. After that, we'll squeeze and pull metal through extrusion and drawing. And we'll finish up by cutting and bending our way through the world of sheet metal. Okay, first things first. Before we can even dream of shaping metal, we have to get a handle on its relationship with heat. Temperature, you see, is the master variable here. It pretty much dictates everything that comes next. It's the real dividing line in the entire world of metalworking. And that dividing line has a name, the recrystallization temperature. Now, I know, it sounds super technical, but the idea is actually pretty simple. Just think of it like a reset button for the inside of the metal. Once you heat a metal above this temperature, its internal structure, these little things called grains, they get all soft and relaxed, ready to be reshaped. This is the key concept for everything else we're going to talk about. So, this brings us to the big choice, hot working versus cold working. If you work the metal above that recrystallization temperature, it's hot working. Below it, you guessed it, cold working. And as you can see here, it's all about trade-offs. Hot working lets you make huge, dramatic changes to the metal's shape, but you might lose a bit of precision. Cold working, on the flip side, gives you amazing accuracy and actually makes the metal stronger, but you can't bend it as much, and boy does it take a lot more force. So let's look a little closer at the benefits of turning up the heat. With hot working, you can make these massive changes in shape without much fuss. What's really cool is that it refines the internal grain structure, which actually improves the metal's mechanical properties. Plus, it squeezes out any tiny little holes in the metal and spreads out impurities, making the whole thing more solid and uniform. But yeah, it's not a perfect system. The biggest headache with hot working is that metal expands when it's hot and shrinks when it cools. That makes it really tough to get your final dimensions just right. You also get this crust of oxidation on the surface called scale, which isn't great. And, it kind of goes without saying that working with red-hot metal and all the gear it requires is pretty difficult and expensive. All right, now that we understand the whole heat situation, let's see how it plays out in our first major shaping process. We're going to talk about shaping by force, and we're starting with the oldest, most classic method there is, forging. Seriously, when you picture a blacksmith hammering away at a piece of steel on an anvil, yep, that's the heart and soul of forging. So why is forging so special? Why is it so strong? Well, it all comes down to this incredible concept called grain flow. And this visual just shows it perfectly. On the left, you see a machined part. See how it just cuts right through the metal's internal fibers? Now look at the right. A forged part forces those fibers to flow and align with the shape of the part itself. This creates this continuous, unbroken internal structure that is unbelievably strong and tough. It's exactly why critical parts, like a crane hook, are always, always forged. Now, forging isn't just one single thing. It's more like a whole family of techniques. You've got the classic smith or hand forging, the blacksmith at the anvil. Then you have the big industrial methods. Drop forging uses the massive impact of a falling hammer. Press forging is more of a slow, controlled squeeze. And upset forging is really cool. It actually gathers material to make a section thicker, which is how you get the heads on bolts and screws. To really see how this works, let's look at a basic forging move called fullering. It's a really simple, elegant process. You just use these two rounded tools, the fullers, to squeeze the hot metal. As you hammer the top fuller, the metal has nowhere to go but out to the sides, which stretches it out and makes it thinner right in that spot. This is one of the fundamental ways you start creating complex shapes from just a simple bar. All right, let's switch gears. We've gone from hammering to, squeezing. I want you to picture squeezing toothpaste from a tube. You apply pressure on one end, and this long, continuous shape comes out the other end, right? Well, that simple idea is the principle behind our next set of processes, extrusion and drawing. Okay, let's make that toothpaste analogy a little more official. Extrusion is pretty much exactly what it sounds like. You take a big chunk of metal, called a billet, put it inside a container, and then use a powerful ram to push it with incredible force through a shaped opening. That's the die. The metal is forced to flow through it, taking on the shape of the die. This is the perfect way to make parts that have the same cross-section all the way down their length, like aluminum window frames or copper pipes. Now, there are two main ways to pull this off. In direct extrusion, the ram pushes the billet and the whole billet slides along the container walls. As you can imagine, that creates a ton of friction. But in indirect extrusion, the die is actually on the end of a hollow ram that pushes into the billet, and the metal flows backward through the hollow part. So what's the big advantage there? Way less friction, which means you need less power to get the job done. So far, all we've talked about is pushing metal, using compressive force. But what happens if we totally flip the script? What if instead of pushing the metal through a die, we try to pull it? And that leads us to drawing. Drawing is all about tensile force, pulling. You take a rod or a wire, you make one end a little pointy, and you literally pull it through a die. Every time it goes through a die, its diameter gets smaller and its length gets longer. This is how we make pretty much every wire you can think of, from the copper wires inside your walls to the steel in a humble paperclip. Okay, for our last section, we're making a big shift. We're moving away from solid blocks and bars and into the world of thin sheets of metal. And this is a huge part of manufacturing that gives us everything from the body panels on your car to the metal case on your washing machine. When it comes to sheet metal, you can really boil it all down to three fundamental types of operations. First, you've got cutting, which is all about separating the material. Then you have bending, which is how you create angles and curves. And finally, you have a process that's also called drawing. Now wait, this is different from the wire drawing we just talked about. In sheet metal, drawing is how you stretch a flat sheet over a form to create a hollow shape, like a kitchen sink or a soda can. So what really happens when you cut sheet metal? It's pretty wild. It's not just a simple slice. It's this high-speed, four-stage event. First, the punch hits the metal and deforms it. Then it starts to penetrate. This creates so much stress that tiny fractures start to form from the sharp edges of both the punch and the die. And finally, those fractures race towards each other and meet in the middle, and the piece just pops right out. All of this happens in a fraction of a second. When it comes to bending, two of the most common ways are V-bending and edge bending. V-bending is about as simple as it gets. A V-shaped punch pushes the sheet into a matching V-shaped die. It's cheap and great for smaller jobs. Edge bending is a little more complex. It uses a pressure pad to clamp the sheet down firmly. Then a punch comes down to make the bend. This gives you way more control over the material. But bending is not as easy as it looks. You see, metal has a kind of memory. After you bend it and let go, some of the elastic energy that's stored up in the part causes it to spring back a little bit. It's a huge challenge for engineers. To get a perfect 90-degree angle, they have to precisely calculate this spring back and actually overbend the part, say to 88 degrees, knowing that it'll relax back to exactly 90. It's a fascinating bit of precision work. And honestly, the world of sheet metal just keeps going with all these specialized techniques. We mentioned drawing, which is how you get deep shapes, like beverage cans. There's stretch forming, where you pull a sheet tight over a die to create huge, smooth curves. Think airplane bodies. You've got spinning, where a flat disc is shaped over a rotating form, almost like making pottery, to create things like light fixtures. And embossing, which stamps in shallow patterns, like lettering or ribs to add strength. The versatility is just incredible. So at the end of the day, when you put it all together, from the intense heat of forging to the delicate dance of sheet metal bending, you start to see that these processes are really the language we use to communicate with metal. They're how we take a raw material and translate it into a functional part, a complex component, and ultimately all the technology that we rely on every single day. And that's where we'll wrap up, but I want to leave you with a little challenge. Go ahead, look around you right now. Find the nearest metal object. Is it a long, uniform shape that looks like an extrusion? Does it look super tough, like it might have been forged? Is it a thin piece that's been cut and bent? Now that you know the basics, can you guess how it was made?